Hello everyone and welcome back. Welcome back to the Mission 30 series. Today we are going to learn the second concept in this Mission 30 system design concept. So in this session we will deep dive to the availability. That is one of the most important concept in system design. In the previous video we learned how to scale a system to handle the increasing traffic. But scaling alone is not enough. A system that can handle million of user is useless if it goes down when a single server fails. So this is where the availability come into the play. So today we are going to take this topic into a very deep dive, and then we are going to discuss this availability concept in by covering all the aspect in terms of system design. So in this video we will mostly focus on the availability. So it is a core concept in system design that determines whether the user can actually access your system when they need it. In the previous video we discussed scalability, how system handle increasing traffic and growing number of users. However, scalability alone does not guarantee a good user experience. So a system that scales to million of user is still a failure if it crashes with a single server goes down. So availability answer a simple but critical question. Is your system still usable when things fail? So real world system. So in the real world, the server will crash, network will fail, the database will go down. So the high available system are designed to survive these failures without affecting the user. So that is where the availability will come into the picture. So if we talk about the definition, the availability means how often a system is up or accessible to the user, right? So there are certain ways, like high available systems are those systems which like continue serve the request even when the individual component fail, so minimizing the downtime and the user visible outage, and also who hide the internal failures through redundancy and failover mechanism. So I hope you know about the redundancy. If you don't know this, then we will talk this later in this session. So an important distinction to understand is that availability is not same as the reliability. Again, if you have not heard this reliability, then we will talk about this in some time. So when you can say that your system is available, so available means always responding to the request, and unreliable means something responding with incorrect or inconsistent data. These are the two terminologies which are very often used in system design: available and unreliable, and both has a different meaning altogether. So in this video, we focus only on keeping the system up, and reliability we'll discuss in the upcoming videos. So stay tuned, hit the subscribe button, and if you want to get the notification, then please subscribe it. And also, like if you like this video or if you learned something new from this session, then please hit the like button so that it will encourage me to create more sessions like this. So let's go ahead and let's understand how to measure the availability. This is the one of the important thing. So availability is usually expressed as the percentage of uptime, right? Over a given period of time. For example, the formula will be like availability equals to uptime divided by uptime plus downtime. So let's take a scenario. For example, if a system runs for an entire year, let's say the uptime is 364 days in a year and downtime is 1 day. Okay. So the availability in the percentage, how it will be calculated by using this formula where uptime is 364 days in 365 divided by 364 uptime plus there was 1 day downtime. So 364 plus 1, that is 365. So 364 divided by 365, that comes near to 99.73%. So what does this mean? It means that one day of downtime does not sound terrible, right, to you, but it already put the system below 3 nines availability. This shows that how strict availability requirement become at scale, especially for critical systems like banking, payment gateways, or the payment applications or large consumer platforms. So this is the formula how which we calculate the availabilities, and then we see that how many nines are coming up. So next topic is the nines of availability. This is the most used terminology in the terms of availability. So let's understand what does 2 9 means, what does 3 nines, 4 nines, 5 nines, 6 nines means in the terms of availability, and why those are important. So availability targets are commonly described using the concept of nine. So each additional nine dramatically reduce the amount of downtime allowed. For example, 99%, which has the 2 nines, allow several days of downtime per year. If you talk like precisely, then it is 3.6 days of downtime per year. So it is acceptable for internal or non-critical systems. And there is, and then the 3 nines, which is 99.9%. It only a few hour of downtime per year, like precisely 8.7 hours per year of downtime, common for many production system, but it is allowed for some production system but not for the critical ones. Then comes the 4 9, it means 99.99 percentage. It means about 52 minutes per year. So now the downtime is reduced to minutes per year. It is precisely 52 minutes per year. Requires carefully design and redundancy, because here we to achieve this 4 9 we need careful design. And the next is 5 9, means 99.999 percentage. It means only few minutes of downtime per year, precisely 5 minutes per year. So these are used by the mission critical systems. Okay, and then comes the 6 9, which is the best in this group, where around 30 seconds per year of downtime. This is really a very low load downtime and a very high availability. So downtime is measured in seconds per year. Okay, for 6 9, and is extremely difficult and expensive to achieve. So as the availability increases, the cost and the complexity of the system also increases significantly. So it depends on your system and the cost, that how much availability is permitted for your application. So I hope you got the idea about this nines. So yeah, so maybe in the interview this will be more helpful for you if you know these like terminologies. Now, next topic is availability in series versus parallel. So, as we are talking in the availability, so we should understand, and the availability total depend on how the component in an application is designed. For example, how components are arranged in a system has a huge impact on an overall availability. For example, components. Okay, so let's first talk about components who are connected in a series. So component are in series when every component must be operational for a system to work. For example, in this diagram you can see we have a web server, then we have a app server, and then we have a database. So web server is 99.9, app server is 99.9, and database again 99.9. And all these components are required to be worked or operational as an whole application. So here, so you can see that all three must be up for request to succeed. So individually they are 99.9% equally. Okay, but when the total availability of a system will be calculated, then you can see on an average it will come down. Since all components are required, their abilities are multiplied together, This result in overall availability of approx 99.7, which is lower than the availability of each individual component. So as the component are added in a series, you can see the chances of failure increases. Downtime become more frequent and user experience more outage. So this is why deep dependency chain reduce the system availability. When the components are connecting in series, it means all the components are required to fulfill the request with a success response. So for that, the availability will go down and the downtime will increase. So this is when the system is connected in a series, right? I hope you understand this. Now let's see the availability if the component of a system are connected in a parallel. Okay, so components are in parallel when any of them can handle the request. For example, here in the diagram you can see we have a two server, server 1, server 2, and these are in parallel with the load balancer. So load balancer will distribute the request to any of the server, right? So server 1 is 99.9, server 2 is 99.9. So for a particular request, that request will be handled either by server 1 or server 2. So if the system fails, only if both the server fail at the same time, which is extremely unlikely. Because of this, the combined availability become very high, approaching to 6.9, right? So parallel design significantly improves the availability and is the foundation of redundancy servers, load balancing, and active-active deployment. Okay, so we will see what is active-active deployment in some time, right? So key takeaway is that availability focus on keeping the system up and accessible. Second, component in series will reduce the availability as we have seen here, and the component which are connected in parallel will increase the availability, right? And like redundancy is essential for building high available system. As here you can see, server 1 and server 2 are redundant. I mean that server 1 and server 2 are duplicated, so any of this will be used for a particular request. So in this way the availability will increase for this, right? I hope you understand this. So before we talk about the availability more, we need to accept one very important truth, that failures are unavoidable. System don't fail only because someone built them badly. So this you need to understand. System fails because modern systems are very complex. Think about it. A system today has a hardware as a hard disk is spinning, right? And the memory is getting like wear and tear. Systems are going up and down. So softwares are getting updated, so software may break with the breaking error, and the humans are operating every time, so there can be human error also. So with so much moving part, so much possibility, something is always at a risk of failing. So now or then the system will fail. They don't wait for the night time, they don't wait for the low traffic. Failures happen during the peak time, during the peak hour, during the deployment, during the important business event. So that's why availability is not about trying to avoid the failure. The real goal is the understand how system fails, and once you understand the common failure patterns, then you design a system that stay up even when things go down, right? So highly available system don't assume nothing will fail, they assume something will fail, and that's okay, we have to take care, we have to handle that. So they are built to expect the failure and survive them, right? So that's the mindset is the foundation of building reliable and always available system. So now let's discuss the common failure modes. So when you understand this, then you can design the better system, because this is very important topic to understand the different type of failures, right? So okay, so let's go ahead. So common failure modes are like first we have a hardware failure. So let's start with a simple truth. anything physical will eventually break. This is the so this is the truth. Not because someone was like careless, not because, but because the physics actually guarantees wear and tear. Because we knew, as per the physics law, if any physical thing is working, so there will be friction, there will be wear and tear by the time, and eventually it will fail. For example, hard disk have the moving part, so they will wear and tear, right? Power supplies handle power supply handle the electricity all the time, so they get stress. Network switches run day and night, so they get tired. So even ssds which don't move can only be written with a limited number of time. So hardware failures is not a surprise, it is inevitable. You might hear a term called mtbf. It means mean time between failures. Many people misunderstand this. MTBF does not mean the server will run perfectly for 10 years. It means if you look of thousand of machines, failures are spread out over time. In a small setup, if 5 to 10 servers, failures feel rare. But in a data center with a thousand of servers where disk fail daily, server suddenly go offline, network port stop working, power supply burn out. This is normal because there are n number of servers are working in a data center. So possibility of failure will be more in that scenario. So here's the key lesson: if your system assume machines will never fail, your system is a weak by design. So you don't need to assume that your system will never fail. You have to assume that system will fail, and you have to design in such a manner that you have a fallback mechanism. You can handle the errors so that you can survive the failure. So good system assumes service will die, disk will fail, network hardware will misbehave. So highly available system treat hardware like a disposal item. The system stays up not because hardware is perfect, but because no single machine is important, right? And here in the chat, you can see in the table. So this is the typical failure rate of some of the component in the physical in the hardware world, like hard disk, that is HSD, has 2 to 4% of failure rate per year, and SSD 0.5 to 1%, servers 2 to 4% per year, network switches 1 to 2% per year, power supply 1 to 3% per year. It means failure possibility is there. So you have to design the system in such a manner, assuming that failure will happen, but you have to overcome it. Okay, you have to survive that failure. You have to design in such a manner. So this is all about a hardware failure. Next is software failure, and this is also very important. Now let's talk about software. If hardware fails randomly, so software fails because human write it. And when human build something, so human will make mistake, right? Let's say a bug can sit quietly for months and suddenly crash the system one day. And the memory leak slowly eats the RAM until the service becomes slow and finally crashes. In a system, in a software, deadlocks happens when two part of a system wait for each other forever and everything looks alive but nothing moves. So the most dangerous type is cascading failure. In the cascading failure, one service becomes slow, other services start sending more requests to it, and then suddenly they are also becoming slow. So slow is spread everywhere. What started as a small issue turns to a fully system outage, right? So in distributed system, this is extra dangerous because the same buggy code runs everywhere. One bad deployment can break hundred of servers at once. That's why availability is not just about redundancy. It also need to be isolate, slow and controlled deployment, ability to quickly roll back the changes. So good system assumes software will fail and they are ready for it. This is about the software failure. Let's move ahead with the network failure. And these are very, very important again to understand. Network failures are most confusing ones. Why? Because network usually don't fail completely. They fail halfway. Sometimes request will work, sometimes they don't. Because packet get dropped randomly, latency suddenly increases, fast operations become slow, timeout start happening. Even worse, network partitions. The system get split into the groups. They can't talk to each other and each group thinks it is fine. So DNS failures are especially painful. If the DNS is down, the service cannot find each other. So that is the most painful. Everything looks broken even though the servers are running perfectly. That's why network issues are hard to debug. Why? Because logs show nothing. Metrics look strange and problems come and go. So strong systems are built assuming that network is slow, network is unreliable, and network will sometimes break. So if you keep these things in your mind and design a system, then you will survive with that failure. So that was pretty much about the network failure. Next is human error, and this is also important to understand. Now come the hardest truth. Human cause most outage. Yes, and believe me, human cause most outage. Not machine, not code, but people. One wrong configuration can take the whole system down. Deploying at a wrong time can overload everything. Running a dangerous command in a wrong environment again can delete the critical data. Underestimating the traffic can crash the system in minutes. So these mistakes don't happen because people are bad. They happen because systems are complex. And as a system grow bigger, the human mistakes become unavoidable. So the good systems are designed with this reality that they use automation instead of the manual steps, test before production, and also easy rollback, and the recovery should be there. So goal is not to stop the human from making mistake. The goal is to limit the damages when mistakes happens. So so the closing part I can say is that failures are not rare in distributed system. They are normal. Hardware will fail, software will break, network will misbehave, and humans will make mistake. After all, they are human, right? So high availability is not about hoping these things won't happen. It is about building system that keep working even they do. Once you understand the failure, you can design the system that user can truly rely on, right? So these are the some type of failure which are common in the world of system. Now let's understand the redundancy, and this is the foundation of availability. Why I say the foundation of availability, let's understand. If there is one idea that sits at the heart of availability, and that is redundancy. Almost every technique used to keep the system available eventually traces back to a single concept. The logic is simple and intuitive. If you have only one instance of a component and it fails, your system immediately goes from 1 to 0. And when you have redundancy, it means failure does not automatically mean outage. If one component fails, another is ready there to take in place. So redundancy means you are keeping the copy of the same component so that if one component will go down, then the other component will be available to take its place. So redundancy means like deliberately having more component that you strictly need for the normal operation, right? Understood? So these extra component are not wastage. They are the insurance. They are the backup. They exist so that the system can continue function when the failures will occur. So without redundancy, availability is nothing more than hope. So redundancy is the most important foundation if you want to achieve the availability, right? So let's go ahead and let's understand some like configurations in the part of like redundancy. So we have active passive, we have active active. So in active passive configurations, what we do in an active passive configurations, only one component is active, which is handling the traffic at any given time, and the other component is considered to be in a standby mode. So the active component is considered the primary or active node, and alongside the other component, the secondary component, will remain ideal or mostly ideal, waiting in the standby mode. So that is known as passive. So standby does not serve the traffic under normal condition. So its sole purpose is to take over when the active component is failed. Okay. So for example, here in the diagram you can see, so this primary server is active, and whenever the failover will come, then the standby server, that is passive, will take care, and then it will work, right? So when the active component become unavailable, then a failover process is triggered, and the traffic is redirect away from the failed component towards the standby, so which is promoted to become the new active component. So from the user perspective, the system may appear briefly unavailable during this transition, but the goal is to minimize the interruption as much as possible. So I hope you understand this, that active passive standby. Um, so basically, active passive setups are very common in system that require a single source of truth. I mean that databases are the classic example for this. Okay, so okay, so let's go ahead to understand the pros and cons for this. Okay, yeah, so like I hope you understand the active passive. In active passive, one is active component and the other is in a standby mode. When the active will go down, failure, then only the standby will come, and then it will handle the request and do the processing. Okay, so let's discuss some pros and cons of active passive. So in this like databases are the classic example for this. Many databases are designed around the idea of a single leader that handles the writes, while the replicas or standbys follows along, right? So where in the database we create the replicas, so there is a primary database which only handles the write operation and the update operation, and the other replicas will handle the read operations. So this model signify consistently and avoid the conflict. This is why often preferred for stateful systems. Okay. So basically the pros are that standby usually consumes a fewer resources, and the cons is that failover take time. So failure detection, promotions, routing update will happen, right? So another risk in active passive system is that the standby may not truly the production ready, because it does not handle the real traffic during the normal operation, because it was in a standby mode. So subtitle issues can go unnoticed until the moment it needed the most. So this can lead to unpleasant surprising during the failover when the backup system fails to perform the under the real load. So this is also the possibility of a split brain scenario where both active and passive components believe they are in charge due to the communication failure. If not handled carefully, this can result in data corruption or inconsistent state. So for active passive, there is a both pros and cons, but you need to understand that which one you means which scenario is beneficial for your use case. All right. So when we talk about a standby, so there are certain labels. Okay, there are cold standby, warm standby, and hot standby. So these are the labels. So not all standbys are equal, because the readiness label of standby determines how quickly it can take over and how much it costs to maintain. So cold by standby is simplest and cheapest form of redundancy. So in this setup, the backup component is powered off and completely inactive. So the standby component will be completely off and it will be completely inactive. When a failure occurs, the system must first start, back up the machine, initialize the service, and restore any required state. So this process can take several minutes, sometimes longer than that. So that's why like cold standby is usually acceptable for disaster recovery scenarios, but it is far too slow for the most production's critical systems where the high availability is very much in a high priority. So this is the one type. So if you are using disaster recovery, then you can use the cold standby mode for active passive configurations. Now the next comes the warm standby. So warm standby strikes a balance between the cost and the speed. So the backup component is running and configured, but it is not actively receiving the traffic. I mean, it may receive replicated data or periodic syncing state from the active component. When the failover occurs, the warm standby can be promoted relatively quicker, often within a second or few minutes than the cold standby. So it is more faster than the cold standby, basically, right? So this approach is commonly in many enterprise systems where short and interruptions are acceptable. Okay. Then come the next, that is hot standby. So a hot standby is the most expensive but also the fastest option. In this configuration, the standby is fully running, fully synchronized, and ready to serve the traffic immediately. Because for databases, this often means that synchronization replications when every write is committed to both the active and standby before being acknowledged to the client. So in this, both the active and passive will be actually active. They are both getting the data, they are both getting the triggered so that it is synced up with the active component. So failovers can happen in second, but the cost is higher resource uses and increase the light latency during the normal operation. So choosing between the cold, warm, and hot standby is always a trade-off between the cost, complexity, and acceptable downtime. So in this diagram, you can see, you can understand this better, that cold standby is cost in low, but failover time is minutes. Warm standby, medium in cost, but second to minutes. Hot standby, failover time in second, it is very quick and but high in cost. So totally it's depend on your scenario which standby mode you are going to use for your system. Okay, so this was all about active passive configurations. Next we are going to discuss active configurations. In an active configurations, all components handle the traffic at the same time. Okay, there is no concept of primary or backup or standby mode. Every node is live, every node is doing real work. Traffic is typically distributed across the nodes using a load balancer. When one node fail in an active system, there is no failover event in the traditional sense. So the load balancer simply stops sending traffic to the failed node, and the remaining nodes continue serving the request and absorb the additional load. From the user perspective, the system often appears completely unaffected. So in active, all the components are active, like server 1, server 2, server 3, all threes are active. If in case if server 1 goes down, then the load balancer always do a health checkup of each of this server. Whoever is down, the load balancer will cut off the communication with that failed server. So the all the traffic will be handled by other two active servers, and they will absorb the tariff or other traffic. Okay, so this is active. So okay, so let's discuss the pros and cons of active. So these models or these configurations offer several major advantages because all nodes are actively serving the traffic. They are continuously tested under the real production condition. Like source utilization is better since no capacity is sitting idle. Important, there is no downtime associated with failover because failover is effectively initiation. Okay, so however, active systems are more complex to design. These are the cons that complex to design and operate. They require careful handling of data consistency, especially for a stateful workload. If multiple nodes can handle the same request, the system must ensure that they all see a consistent view of data. And this is often required in shared storage system, distributed databases, and in-memory data storage like Redis, right? So active designs also work best when servers are stateless. Stateless service can handle any request independently, making them ideal candidate for this model. And stateful service can still use active pattern, but they require additional coordination mechanism which increase the complexity. So I hope you understand active passive and active with their pros and cons, which will help you to understand the system. The next is statelessness and the shared state. Okay, so this is also very important topic in the field of availability in the system design, as the success of active architecture depend heavily on how state is managed. Stateless service naturally fit this model because they do not depend on the local memory or disk to process the request. Any node can handle any request, making the failure largely invisible. For on the other side, for stateful service, the state must live outside the individual node. So this often means using a shared database, distributed cache, or external storage system. In some cases, sticky sessions are used to route user to the same node repeatedly, but this reduce the availability benefit of active active design and can reintroduce the single point of failure, right? So redundancy is not an like optional feature of heavily available system, but it is the foundation on which everything else is built, whether through the active passive setups with a carefully managed failovers or active architectures with a load balancer traffic, right? So availability is not achieved by preventing failure, it is achieved by making failure survivor. Okay, and redundancy is how system stay alive when individual component inevitable fails. So I hope you understand this. Now, next is geographical redundancy and layered availability. So this is the type of redundancy in which we will talk about the geographic. So when we talk about redundancy, many systems start by adding backups inside a single data center. So this protect us from the common problem like server crashing, disk failing, or switch going down. However, this approach has a big spot. What if the entire center fails? The whole data centers can go offline, right? Due to the power outage, due to the internet backbone or the fire cable cut, maybe due to the natural disasters like flood, earthquakes, right? Or it may also go to the human errors. What if someone digging and cutting a major cable? When this happens, every server inside the data center become unavailable at the same time, no matter how well the design it is. So how you will solve this? You can solve this by using a geographic redundancy. So geographic redundancy means running the same system into the multiple physical locations, often in different cities, countries, or con- maybe continent. If one location goes down, traffic can be routed to the another location that is still healthy. So user don't do like directly connect to the specific data center. Instead, they connect through the global routing layer, that is we call as a DNS, which automatically send them to the nearest to the healthiest location. For example, here in the diagram you can see that user is connecting not to the directly to the different geographics, but they are connecting to global DNS, which is further transferring the traffic to the different geographics. For example, this US East, US West, and Europe. These are the different geographic areas. Okay, and every geographic has their system, and there are like availability zones. Like availability zone 1 is US East, and availability zone 2 is US West, 3 is Europe, right? So yeah, so I hope you understand the geographical redundancy and why it is important. It is important. What if the data center as a whole will go down? In that thing, what you will do? In that, geographical redundancy is helpful. So now let's understand the terms inside this geographical redundancy. For example, uh, the cloud redundancy models. So we have like availability zones, which we called represent as AZ, and then we have the reasons, and then we have a multi-cloud. Okay, so first we will talk about the availability zone. So cloud provider divide a region into multiple availability zones that we terms as AG. And availability zone is a separate data center within own power supply, cooling system, and network connectivity. Even though the AGs are isolated, they are connected very fast, low latency networks. So why it is important? Why availability zones are very important? If one AG fail, the application can immediately shift to the traffic to the another AG without noticeable delay to the user. And latency between the AG is typically 1 to 2 million, which is a very low enough to allow synchronous communication between the service and database. So here in the diagram you can see, what if the US East goes down, this available zone goes down, then the traffic will distributed to the availability zone 2 or availability zone 3. In this, the switching is so very much fast that the delay of 1 to 2 milliseconds, which is like considerable in this case, right? So this make availability zone the most practical and the cost effective choice for the most application, right? So next is reason. So what is reason? Reason is a geographical separate area such as US East, US West, or Europe. So region are far apart, often thousands of kilometers from each other. The advantage of region is strong isolation. One region going down does not affect the another, and the protection from large scale outage and disaster. So the trade-off is latency. The network delay between the region is very high, so usually 50 to 100 milliseconds or more. It means someone having um doing a request to the US East will get the low latency if the server is in the US East. And if someone is doing the request from US East, and if the US East is down, the server is down, then if it goes to the Europe, then of course the latency will increase, right? So yeah, that's why these things are important to understand. So this means that system must stay fast, and with a small amount of recent data may be lost during the major disasters. Okay. The next terminology is multi-cloud. Okay. So multi-cloud means deploying the same system on a different cloud providers, such as maybe you can deploy to AWS or to the Google cloud provider, that is GCP, or maybe to the Azure, right? So this approach protect against a full cloud provider outage. What if the AWS is down? What if the Google is down? Then you will have the other partners, which is the cloud provider. From there, it will handle. So cloud specific bugs or service disrupt. So it will handle all those things. So, however, multi-cloud comes with a high complexity because different APIs and service, due to the different networking models, more operational overload will come. Because of this, multi-cloud is usually used only for a very critical system, such as maybe to the finance domain or to the global enterprise where the critical systems are running out. Okay, so I hope you understand this topic, cloud, like cloud redundancy models. Next, we are going to see the redundancy across layers and reality check. Okay. So high availability is not achieved by just adding the redundancy at only one place. I mean, each layer must be redundant. I mean, the DNS should also be like redundant, load balancer, application server, database. If any one layer is not redundant, and what if it becomes fail, then it is the only single point of failure. So we should not always be make system as a single point of failure for any component. For example, multi-application servers are useless if there is only one database. And what if that database get failed? Then your whole system will fail, right? So there is no point of adding like redundancy to the other components, right? So that's why adding the redundancy across all the layers is very, very important. So, okay. So next we are going to see. Okay, so high available patterns. Okay, so redundancy is not free because it comes with the extra cost like server, database replicas, availability zones, reason. All these things are adding the cost. So real system design question is the okay. So is the cost redundancy lower than the cost of downtime? Okay, so this should be the question. So next we are going to see the high availability patterns. Okay, so in this system the patterns are like the lesson learned from the real failures. Okay, so high availability patterns means basically engineers across the world faces the same problem again and again. Okay, like the server crashes, database goes down, traffic suddenly spikes, and like one service start failing and bringing down the other with it. So other over the time, certain solutions are proved to work to give the reliability. So these solutions are called high availability patterns. For example, they help the system to stay online when the part of the system are broken. So here we means use certain patterns which help for the high availability. For example, the first pattern we will discuss is load balancer with multiple backend. So imagine a website that's run only one server. What if that server get crash? The website immediately goes down from everywhere, for everyone basically. To avoid this, modern system never rely on a single server. Instead, they run multiple copies of same application and put a load balancer in front of them. So users send their request to the load balancer and not directly to the servers. So load balancer work is to act as a traffic police to, so it receive the request and forward it to one of the available servers. So all servers do the same job. So it does not matter that which one will receive the request and who is handling the a request. So it is the load balancer who decide that which server will fulfill the request. Okay. So load balancer also continuously check whether each server is healthy. If server stop responding or returns error, the load balancer automatically stops sending the traffic to that particular server. Okay, so here user are silently redirecting to remaining healthy servers, but user will not know that which server is fulfilling the user request. So this happens within a second and usually without anyone like noticing. So when our traffic increases, new server can be added. While the system is running, the load balancer immediately start using them. And because of this, system stay available even when the server fail or traffic suddenly increases. Right? So here in the diagram you can see it checks the health and it keeps on checking the health, and whoever is down it will not transfer the traffic to those servers, right? So next is load balancer redundancy. So till now we have seen that we have done the redundancy for the servers, But load balancer redundancy is also important. While a load balancer improves the availability, it introduces a new problem. If there is only one load balancer and it fails, the entire system becomes unreachable, right? In this case, the load balancer itself becomes the single point of failure. So to solve this, highly available system use more than one load balancer, and one load balancer actively handles the traffic while the other waits in a standby mode, right? So in a cloud environment, this complexity is hidden from the developers, right? So cloud load balancers are already distributed and redundant behind the scene. And in on-premise environment, engineers manually configure the failovers using the tools to move the virtual IP between the load balancer. So either way, goal is the same. Users should not lose access just because one load balancer failed. So in this, we create the copy of load balancer, and there are multiple load balancers who handles the traffic. Okay, so this is about the load balancer redundancy, and this is also very very important. In the diagram you can see that we have added two load balancer, one in active mode, one in standby mode. When the active mode load balancer fails, then the standby load balancer will start working on, and then it will transfer the request to the server as the active was doing. Okay, so this is about the first pattern, that is a load balancer. The second pattern we are going to discuss, that is a database replication with automatic failover. So databases are different from application server, right? Application servers are usually stateless. It means that it does not have any state. But database store the critical data. Because of this, database cannot simply be load balanced in the same way. So to keep database highly available, system use replications. One database act as a primary and handle all the writes, and the other database act as a replicas and continuously copy the data from primary to the applications. Okay, and applications usually read from replicas and write to the primary, right? So basically a monitoring component constantly check the health of the primary database. If the primary fails, one of the replicas is automatically promoted to become the new primary. So the application reconnect to the new primary and continue working with a minimal downtime. So this process is called automatic failover. Okay, without database failures could require manual intervention and causing the long outage. I hope you understand. So in the diagram you can see that we have splitted or created a replicas of DB. So primary DB is used to write operations mostly, and the replicas are the copy of the primary DB, and they are mostly doing the read operations. What if the primary DB goes down? Then the so the one of the replicas will become the primary, and then it will configured and again starting working as the earlier. So this is called as a failover, right? I hope you understand this. Next is synchronous versus asynchronous replication, and this is also very important. So replication can happen in different ways. In synchronous replication, a write is not considered complete until both the primary and replicas confirm it, right? So this guarantee that no data is lost. Even if the primary fails immediately, the downside is that every write becomes slower because it must wait for the replicas to become the primary, and then to I mean and to save the data, right? So in asynchronous replicas, the primary confirms the write immediately and send the data to replicas later. So in synchronous, both the primary and replicas will update the data and send back the like trigger. But in asynchronous, primary confirms the write operation immediately and data to the replicas will update later. So this keep the system fast but introduce a risk of data loss, or you can say the replication lag. So if the primary caches before the replicas catch up, some recent data may be lost. Okay, so because of this trade-off, most production system combine both the approaches, and they use synchronous replication for replicas that will take over during the failover, and asynchronous replication for reading, scaling, and analytics. So this balance performs safely and available, right? So next pattern, yeah, so this we discussed already. So next pattern is queue based loading labeling. So some system receives traffic in unpredictable burst. For example, a flash sale might suddenly generate the thousand of requests per second. If all these requests directly hits the database can become overwhelmed and crash. So queue-based loading labeling solve this problem by introducing a buffer between the incoming processing and the real processing. So between the incoming request and the processing. So there will be the messaging queue, which can be implemented using a Kafka or a Rabbit queue or SQS. So instead of processing the request immediately, the system will place them into the queue, and the worker processes then consume the message from the queue at a steady or controlled rate. Even if the traffic suddenly increases, the queue absorbs the spike. Database continue to receive the request at a same pace, right? So if a worker crashes, the message is not lost and can be processed again by the another worker, right? So this pattern allows system to stay available under extreme load without overloading the downstream services, right? I hope you understand this queue based loading labeling. Just you add one message queue which will observe the spike, and the worker servers will consume the request at its phase, and it will connect to db at its own phase. Okay. So next pattern is circuit breaker, and this is important. So when one service depend on another service, failures can spread quickly, right? If the downstream service start failing, continuing to call it waste resource and slow down the entire system. So over time, this can cause a chain reaction, and the cascade failure will happen. So multiple service will fail. So circuit breaker pattern prevent this by stopping the request to a failing dependency. Initially, request flow normally. If the failure cross a certain threshold, the circuit breaker will open and immediately reject the new request. So this protect the system from wasting time and the resources, right? So after a short wait, circuit breaker allows a few test requests again to check whether the dependencies has recovered or not. If the test succeed, the normal traffic resumes. If it fails, the circuit breaker open again. By failing fast, the system remains responsive and avoid the cascading failure, right? So circuit breaker is very very important to escape from or avoid from the cascaded failures, right? So whenever the service are down, so the circuit breaker keeps on check if and it hits the sample test a request. If in case the service is still not responding, then it will keep the circuit breaker open. So this will stop spreading the failure to the other services also. Okay. So there are three states for the circuit breaker as closed, open, and half open. So closed means normal operation, all requests pass through and failure rate is monitorized. In open, dependency is considered unhealthy, request fail immediately, no call are made to the failing service. And then half open, so limited test requests are allowed. If test succeed, then it is closed. If test fail, then again it is open. So circuit breaker has three state, and these are important: that close, open, half open. Close when normal operations is happening. Open when failures are there. Half open, it is means circuit breaker is testing it. If it fails, then it open. If succeed, then close. Okay. I hope you understand the circuit breaker. Next is availability versus reliability. So which we discuss in the very starting, what is reliability, right? So a high availability means the system is up and responding, but availability alone is not enough. As we discuss, system that respond quickly but returns incorrect result then cannot be trusted, and that is a problem. So if it is responding, then it should respond with the correct data. right? So that is why the next step after the availability is the reliability. And the reliability ensure the system is not only stay online but also produce the correct and consistent result even during the failure, right? So which we are going to see in the upcoming lectures about the reliability. So I hope you learn something new from this topic, and if yes, then please hit the like button so that it will motivate me. And also don't forget to subscribe